So here's the picture, and I won't any more explain what's in it, but except there's the mass, here is the spring constant, the spring with its constant here, here is the dashpot with its constant. The equation is from Newton's law, mx double, so this will be x, and here's, let's say, his equilibrium point is over here. It looks like mx double prime, we derived this last time, plus cx prime plus kx equals 0. And now if I put that in standard form, it's going to look like x double prime plus c over m x prime plus k over m times x equals 0. And finally, the standard form in which your book writes it, which is good, that it's a standard form in general that is used in the science and engineering courses. One writes this as, just to be perverse, I'm going to change x back to y, okay? So mostly just to be eclectic, to get you used to every conceivable notation. So I'm going to write this as change x to y, so that's going to be on y double prime. And now this is given a new name, p, except to get rid of lots of 2's, which would really screw up the formulas, make it 2p. You'll see why in a minute. So there's 2p times y prime, and this thing we're going to call omega naught squared. Now that's okay, it's a positive number. Any positive number is the square of some other positive number, you know, take its square root. You'll see why, to make the, it just makes the formulas much pretty to call it that. And it makes it also a lot of things much easier to remember. So all I'm doing is changing the names of the constants in that way in order to get better formulas, easier to remember formulas at the end. Okay, now we're interested in the case where there's oscillations. In other words, I only care about the case in which this has complex roots, because if it has just real roots, that's the overdamped case. I don't get any oscillations. It's by far, oscillations is by far the more important of the cases, two cases. I mean, just because, I don't know, I could go on for 5 minutes listing things that oscillate. Oscillations, you know, like this, or they could oscillate by going to sleep and waking up and going to sleep and waking up. They could oscillate, okay, so that means we're going to get complex roots. The characteristic equation is going to be r squared plus 2p. So p is a constant now, right? Often p I use in this position to indicate a function of t, but here p is a constant. So r squared plus 2p times r plus omega naught squared is equal to 0. Now what are its roots? Well, you see right away the first advantage in putting in the 2 there. When I use the quadratic formula, it's negative 2p over 2. Remember that 2 in the denominator. So that's simply negative p. And how about the rest? Plus or minus the square root of, now do it in your head, b squared, 4p squared minus 4 omega naught squared. So there's a 4 in both of those terms. When I pull it outside, it becomes a 2. And then the 2 in the denominator is lurking, waiting to annihilate it. So that 2 disappears entirely, and what we're left with is simply p squared minus omega naught squared. Now, whenever people write quadratic equations and arbitrarily put a 2 in there, it's because they're going to want to solve the quadratic equation using the quadratic formula, and they don't want all those 2's and 4's to be cluttering up the formula. That's what we're doing here. Okay, now the first case is where p is equal to 0. This is going to explain immediately why I wrote that omega naught squared, as you probably already know from physics. If p is equal to 0, the mass isn't 0, otherwise nothing good would be happening here. It must be that the damping is 0. So p is equal to 0 corresponds to undamped there is no dash pot. The oscillations are undamped, and the equation then becomes, the solutions then are, well, the equation becomes the equation of simple harmonic motion, which I think you already are used to writing in this form. And the reason you're writing in this form, because you know when you do that, this becomes the circular frequency of the oscillations. The solutions are pure oscillations, and omega naught is their circular frequency. So right away from the equation itself, if you write it in this form, you can read off what the frequency of the solutions is going to be, the circular frequency of the solutions. Now, the solutions themselves, of course, look like, the general solutions look like y equal, in this particular case, there is no, the p part is 0, this is 0, it's simply, so in this case, r is equal to omega naught I times omega naught, plus or minus, but as before, we don't bother with a minus sign since one of those roots is good enough. And then the solutions are simply C1 cosine omega naught t plus C2 sine omega naught t. That's if you write it out in the sign, and if you write it using the trigonometric identity, then the other way of writing it is that A times the cosine of omega naught t, but now you'll have to put in a phase lag. So you have those two forms of writing it, and I assume you remember the little triangle which converts one into the other. Okay, so this justifies calling this omega naught squared rather than k over m.